stop with this. Okay, I'm gonna finish up capacitance this week as well. So we're still covering 1.5 chapters per week. Speaking of capacitance, if somebody's having a heart attack, they use the defibrillators, right? So what does a defibrillator do? It shocks the heart. It stops the heart for a fraction of a second. What does it take to stop a heart? Heart is an electrical device, organ, more like it. So if you shock it with 1 amp of current, you can actually stop it. So what does it take to stop the heart? It takes 1 amp of current. That's all it takes. So you stop it for a fraction of a second, and it resets itself. Okay, so that's the idea behind defibrillator. All right, but here's the trick though. You have to pump about 20 amps of current into the heart within a fraction of a second. That's like 1,000th of a second. So it's crucial that you pump this amount of current within this amount of time. The timing is everything, because 20 amps of current is also the amount of current which is applied to a person under electric chair. So what's the difference between a guy whose life you're trying to rescue and the guy that you're trying to kill? It's the duration of the current. All right, well, the guy's on the electric chair, tough shit. It's about 2, 3, 4 seconds long. All right, and the person that you're trying to save, the current needs to be administered only about 1,000th of a second, no more than that. And then also you're using a defibrillator, meaning that you need to be able to charge it up, and you need to be able to administer the charge, this amount of charge, exactly within this time period. You're not trying to cook the heart, you're just trying to restart it. So here's a question for you. So what does it take to stop the heart? It's 1 amp of current, that's just 1. So if it takes 1 amp of current, why pump 20 amps of current into the chest cavity? Any ideas, any suggestions? Why are they pumping 20 amps of current into the chest cavity? All right, so what do you guys think?
Not all of it's going to go through the heart. Okay,
I'm going to give you 5 points. Guys, this was a huge problem that happened during the first execution of the electric chair roughly 100 years ago in Buffalo, New York. And they advertised, they sold the idea to this poor guy. They said, hey, we can kill you without causing any pain or undue pain or suffering. And, you know, we will just turn on the circuit and then pump the current in. You're not going to feel a thing. You'll be dead within a few seconds without any pain or undue suffering. And then they did a good job in selling the idea, so the guy volunteered. Except, as you will find out, the execution took minutes. By the time it was done with, the person was already on fire. So it was complicated. So what complicated it was that the target organ that they were trying to attack was the heart. And then they noticed that getting to the heart is not that easy, because it's located deep within the body cavity. And then you literally have to pump about 20 amps of current into the body. And then if you're lucky, a decent amp of current is going to get there. So the current is going to dissipate. What do you have? You got the muscles, you got fat, you got internal organs in between. So if you're lucky, you pump 20 amps of current. If you're lucky, 1 amp of current is going to get to the heart and stop it momentarily. And then the person's heart is going to start to beat. So how do you control the discharge time? And where do you store this amount of charge? How does that work out? All right, so again, the same question. You got a flash, and notice that this flash is being activated within a 10th of a microsecond. Okay, so that you can actually see a bullet go through a banana in this case. All right, so how do you get to discharge something within a controlled amount of time? Guys, we're talking about lightning and controlling lightning in this case. All right, notice that we went from the unpredictable lightning to a predictable lightning under the circumstances. What makes lightning phenomena so unpredictable was the charge distribution is not uniform. What makes this sort of lightning, the flash, predictable is the fact that we will have a predictable uniform charge distribution. All right, so there are 2 things you need to be able to do. Number 1, you need to be able to store up the proper amount of charge. Number 2, you're supposed to be able to administer that charge within a controlled time period. You literally are dealing with mini lightning, and every aspect of motion is 100% predictable. You're trying to save a life, it needs to be 100% predictable. You're taking a picture like that, it needs to be 100% predictable. So that charge storage device is known as a capacitor, and that's what we're dealing with. All right, so let's briefly go through the history of capacitors.
So Franklin decided to use the power of reason to rationally explain what many considered a magical phenomenon, lightning. This is probably one of the most famous scientific images of the 18th century. It shows Benjamin Franklin, the heroic scientist, flying a kite in a storm, proving that lightning is electrical. But although Franklin proposed this experiment, he almost certainly never performed it.
Much more likely is that his most significant experiment was another one, which he proposed but didn't even conduct. In fact, it didn't even happen in America. It took place here in a small village north of Paris called Marly-les-Ville.
The French adored Franklin, especially his anti-British politics, and they took it upon themselves to perform his other lightning experiments without him. I've come to the very spot where that experiment took place.
In May 1752, Georges-Louis Leclerc, known across France as the Comte de Buffon, and his friend Thomas-Francois Delibar erected a 40-foot metal pole more than twice as high as this one, held in place by 3 wooden staves just outside Delibar's house here in Marly-le-Ville. The metal pole rested at the bottom inside an empty wine bottle.
Franklin's big idea had been that the long pole would capture the lightning, pass it down the metal rod, and store it in the wine bottle at the base, which worked as a Leyden jar. Then he could confirm what lightning actually was. All his French followers had to do was wait for a storm. And then on May 23rd, the heavens opened.
At 12:20, a loud thunderclap was heard as lightning hit the top of the pole. An assistant ran to the bottle. A spark leapt across between the metal and his finger, with a loud crack and a sulphurous smell, burning his hand.
The spark revealed lightning for what it really was. It was the same as the electricity made by man.
It's hard to overestimate the significance of this moment. Nature had been mastered. Not only that, but the wrath of God itself had been brought under the control of mankind. It was a kind of heresy.
Franklin's experiment was very important because it showed that lightning storms produce or are produced by electricity, and that you can bring this electricity down. Electricity is a force of nature that's waiting out there to be tapped.
All right, so that was your lightning in a bottle.
Next, Franklin turned his rational mind to another question. Why the Leyden jar made the biggest sparks when it was held in the hand? Why didn't all the electricity just drain away? And drawing on his experience as a successful businessman, he saw something no one else had. That, like money in a bank, electricity can be in credit, what he called positive, or debit, negative.
For him, the problem of the Leyden jar is the problem of accountancy. Franklin's idea was every body has around it an electrical atmosphere and a natural amount of electric fluid around each body. If there's too much, we'll call it positive. If there's too little, we'll call it negative. And nature is organized so the positives and the negatives always want to balance out, like an ideal American economy.
Franklin's insight was that electricity was actually just positive charge flowing to cancel out negative charge, and he believed this simple idea could solve the mystery of the Leyden jar. As the jar is charged up, negative electrical charge is poured down the wire and into the water. If the jar rests on an insulator, a small amount builds up in the water. But if instead the jar is held by someone as it's being charged, positive electric charge is sucked up through their body from the ground to the outside of the jar, trying to cancel out the negative charge inside. But the positive and negative charges are stopped from cancelling out by the glass, which acts as an insulator.
Okay, notice that all of a sudden this turns into a lightning jar, turns into a charge storage device. It turns into a capacitor. All right, so positive charges are on the outside, the negative charges are on the inside.
So instead, the charge
So you got equal number of positive and negative charges on both sides of the divide. In this case, it's the glass.
grows and grows on both sides of the glass. Then, touching the top of the jar with the other hand completes a circuit, allowing the negative charge on the inside to pass through the hand to the positive on the outside,
You get a discharge.
finally cancelling it out. The movement of this charge causes a massive shock and often a spark.
The modern equivalent of the Leyden jar is this, the capacitor, and it's one of the most ubiquitous of electronic components. It's found everywhere. There are a number of smaller ones scattered around on this circuit board from a computer.
They help smooth out electrical surges, protecting sensitive components, even in the most modern.
Okay, cute. All right, guys, your quiz is gonna start in about a minute. If you have any questions, just stick around. Hold on to your participation points once again. All right, and I will be back at 9:20. All right, so if you have any questions, just stick around. If not, I'll see you guys tomorrow. Here, I guess. All right, so when somebody's having a heart attack, it's 20 amps of current for a fraction of a second, like a thousandth of a second. That's how much current is being pumped into the body cavity. It takes about an amp of current to stop the heart and restart it. So resetting the heart takes about an amp of current. Question is this. How do you control the discharge time? Notice that in this case, the discharge time is about 2,000th of a second. It's controlled lightning. It's 100% predictable. How do you make something like lightning, which happens to be an unpredictable phenomenon, and kind of bottle it up and turn it into a predictable phenomenon, something of a predictable phenomenon? How does that happen? All right, this becomes possible if you can actually store up the charge, and which means that you should be able to control the charge up time as well as the discharge time. So how do we get to do that? Once again, this flash photography. Notice that the discharge takes place within 0.3 of a millionth of a second. All right, so how do we actually get to control that? All right, so we were talking about capacitors. Speaking of capacitors, what is a capacitor? All right, so capacitor is a charge holding device. A simple capacitor that we can think of is a parallel plate capacitor, which means that it's going to have two plates. And we're going to get to charge up one plate positively. The other plate is going to be negatively charged up. All right, so one plate is being positively charged, the other plate is negatively charged. The way we do it is we usually use a battery in order to do that. All right, so this one is your capacitor symbol. There's going to be a switch involved. There's a battery. So by hooking the capacitor up to your battery, you can charge one side positively and the other side negatively. Here's your battery. All right, so the positive one is going to be connected to C, and the negative one is connected to the one on the right. So it gets charged up.